Soviet engineers thought American aircraft designers had lost their minds, strapping rocket engines to ordinary fighter planes and expecting pilots to survive. One afternoon in 1944, with experimental technology and desperate innovation, they created what would become one of the most terrifying interceptors in aviation history. Captain Harold Fisher of the United States Army Air Force stood before a standard P-51 Mustang fighter that had been radically modified with something unprecedented, a massive rocket engine mounted beneath the fuselage. "They want us to light this thing in flight?" he asked the engineering team incredulously. "At what point does this stop being an airplane and become a missile with a pilot?" His skepticism seemed justified, but the story of why American engineers did this and what effect it had reveals something profound about technological desperation, the psychology of speed, and the bizarre innovations that emerge when conventional solutions fail. What started as a seemingly insane experiment by a handful of engineers would force Soviet aircraft designers to completely rethink what was possible in aviation. The concept of rocket-assisted aircraft didn't emerge from careful peacetime research and development. It emerged from desperate wartime necessity when conventional solutions proved inadequate. By 1943, American bomber formations were suffering catastrophic losses over Germany. Luftwaffe fighters, particularly the Focke-Wulf FW-190 and Messerschmitt Bf-109G, were decimating bomber streams despite fighter escorts. The problem was altitude and interception time. German fighters would climb above bomber formations, sometimes to 30,000 feet or higher, then dive through the formation at speeds exceeding 400 miles per hour. By the time American escort fighters could react and climb to intercept, the German fighters had already attacked and disengaged. Conventional fighter aircraft, even the excellent P-51 Mustang, couldn't climb fast enough to intercept these high-altitude diving attacks. American aircraft designers faced a fundamental problem. To intercept high-altitude attacks, fighters needed dramatically improved climb rates, but improving climb rate through conventional means meant larger engines, which meant heavier aircraft, which negated the performance gains. It was an engineering paradox that seemed impossible to solve through conventional approaches. Then, someone suggested something that sounded completely insane: temporarily augment fighter engines with rocket propulsion. Not replace the conventional engine, but supplement it with short-duration rocket boost that would provide explosive climbing performance when needed. The concept violated every principle of conservative aircraft design. Rockets were temperamental, dangerous, and consumed fuel at absurd rates. Mounting volatile rocket engines on aircraft carrying pilots seemed suicidal. But desperation breeds innovation. American engineers began experimenting with rocket-assisted takeoff units, small solid-fuel rockets that helped heavy bombers get airborne from short runways. If rockets could help bombers take off, perhaps they could help fighters climb. The theoretical possibility existed. The practical challenges were enormous. Stay with me. We're about to reveal the first attempts to turn this insane idea into reality, and the results shocked everyone involved. The initial American experiments with rocket-assisted fighters began in 1943 under conditions of extreme secrecy. The program was designated Project M X-324 and involved multiple aircraft manufacturers, engine companies, and military test pilots willing to risk their lives testing fundamentally unproven technology. The first attempts used solid-fuel rockets mounted externally on existing fighter aircraft. Republic P-47 Thunderbolts received experimental installations where solid-fuel rocket units were attached beneath the fuselage or on wing hardpoints. The concept was straightforward. The pilot would activate the rockets when maximum climb performance was needed, gain altitude rapidly, then jettison the spent rocket units before engaging enemy fighters. The initial test flights were terrifying. Captain John Myers, one of the first test pilots to fly a rocket-augmented P-47, described the experience in clinical terms that barely concealed his fear. The rockets ignited with a violence that was genuinely shocking. The acceleration was unlike anything I'd experienced in conventional aircraft. We went from level flight to nearly vertical climb in seconds. The G-forces were at the edge of tolerable, but the handling was unpredictable. The thrust wasn't perfectly aligned, which created yaw moments that required constant correction. And the psychological factor of knowing you're sitting in front of a volatile chemical reaction was significant. These early solid fuel systems had severe limitations. The burn time was extremely short, typically 30 to 60 seconds. The thrust was inconsistent and couldn't be controlled once ignited. The rockets added substantial weight and drag even when not firing. And the safety concerns were profound. Solid fuel rockets occasionally exploded catastrophically, and several test aircraft were lost to rocket malfunctions. But the performance gains were undeniable. A P-47 with rocket assist could achieve climb rates exceeding 6,000 feet per minute, nearly double the conventional climb rate. If this technology could be refined and made reliable, it could provide exactly the interception capability American fighters desperately needed. The program expanded to include liquid fuel rocket systems, which offered controllable thrust and better performance characteristics. Bell Aircraft, the company that would later produce the X-1 that broke the sound barrier, developed a revolutionary liquid fuel rocket engine designated the XLR-11. This engine used ethyl alcohol and liquid oxygen as propellants and could be throttled and restarted in flight, unlike solid fuel systems. Technical Sergeant Robert Williams, a crew chief working on the rocket fighter program, explained the engineering challenges. Liquid fuel rockets were incredibly temperamental. The propellants were dangerous. Liquid oxygen is viciously cold and volatile. The fuel systems had to be absolutely perfect, because any leak could cause catastrophic fire or explosion. We were essentially building bombs that pilots would intentionally detonate while sitting on top of them. The engineers assured us it was safe. We weren't entirely convinced. But here's where the story takes an unexpected turn. Hang tight. The Germans were developing their own rocket fighters, and what American intelligence discovered changed everything. While American engineers were experimenting with rocket-assisted conventional fighters, German engineers were developing something far more radical: purpose-built rocket-powered interceptors. Intelligence reports reaching the United States in late 1943 and early 1944 described German aircraft that sounded like science fiction. The Messerschmitt Me-163 Comet was a tailless rocket-powered interceptor unlike anything in Allied arsenals. It had no conventional engine whatsoever, only a Walter H.W. Quenda 09-509 rocket engine, burning an exotic and incredibly dangerous fuel combination designated C-STOF and T-STOF. The aircraft could climb to 30,000 feet in under 3 minutes and achieve speeds exceeding 600 miles per hour, far faster than any Allied fighter. American intelligence officers initially dismissed these reports as exaggerated or propaganda. The described performance seemed physically impossible, but photographic reconnaissance confirmed the aircraft's existence, and captured Luftwaffe documents revealed that the Me-163 was operational and shooting down American bombers. This intelligence created panic in American aviation circles. If Germany had operational rocket fighters with such dramatic performance advantages, Allied air superiority was threatened. The Me-163's combination of speed and climb rate made it nearly impossible to intercept using conventional fighters. It could climb above bomber formations, attack at speeds too fast for gunners to track, then glide back to base before escort fighters could respond. The American rocket fighter program, previously viewed as experimental and low priority, suddenly became urgent. The perceived need to counter the German rocket threat drove massive increases in funding, resources, and priority. Multiple parallel programs accelerated development of American rocket-powered and rocket-assisted aircraft. But American engineers made a crucial decision that would differentiate their approach from German methods. Rather than developing pure rocket fighters like the Me-163, which had extremely short-powered flight duration and numerous operational limitations, Americans focused on hybrid systems that combined conventional engines with supplemental rocket propulsion. Major Robert Cardenas, assigned to evaluate captured German rocket technology after the war, explained the American reasoning. The Me-163 was an impressive technical achievement, but a tactical nightmare. It had perhaps 8 minutes of powered flight before fuel exhaustion, which gave it one attack pass before becoming a vulnerable glider. The fuel was so dangerous that ground crew casualties from handling accidents exceeded pilot casualties from combat. The landing approach as an unpowered glider was extraordinarily dangerous. The Germans had created a high-performance interceptor that was almost as dangerous to its own pilots as to enemy bombers. American hybrid approach aimed for practicality over pure performance. A conventional fighter with supplemental rocket boost could operate normally most of the time, use rocket power only when needed for maximum performance, then continue fighting with conventional engine power. This provided operational flexibility the pure rocket fighters lacked. The most successful American implementation was the Republic P-47M Thunderbolt, with the War Emergency Power System augmented by experimental rocket boosters. Keep going. We're about to see how Soviet observers reacted when they witnessed this technology, and their response was remarkable. Soviet military observers were embedded with American forces in Europe as part of the alliance against Germany. These observers reported everything they saw back to Soviet aviation authorities. When they first witnessed rocket-assisted American fighters in late 1944, their reports reflected genuine astonishment and skepticism. Colonel Mikhail Gromov, a decorated Soviet test pilot serving as a military observer, filed a report after witnessing trials of rocket-assisted P-47s that captured the Soviet perspective. The Americans have developed aircraft that temporarily employ rocket propulsion to achieve extraordinary climb rates. The engineering is sophisticated, but seems unnecessarily complex. The tactical utility is questionable. Soviet fighters achieve adequate interception capability through conventional means without resorting to dangerous experimental systems. This appears to be another example of American tendency toward technological excess rather than practical simplicity. This dismissive assessment reflected broader Soviet design philosophy. Soviet aircraft designers prized simplicity, ruggedness, and ease of maintenance. Soviet fighters were designed to operate from primitive airfields with minimal ground support. Complex systems requiring specialized maintenance and exotic fuels were considered operationally impractical, regardless of performance advantages. But Soviet attitudes began changing when they examined captured German Me-163 rocket fighters and studied the tactical implications. Soviet engineers realized that rocket propulsion offered performance impossible to achieve through conventional means. A conventional fighter, no matter how well designed, was limited by propeller efficiency, engine power-to-weight ratios, and aerodynamic constraints. The rockets bypassed these limitations entirely. The captured Me-163 aircraft were extensively studied by Soviet engineers. Despite initial skepticism, they recognized the revolutionary nature of rocket propulsion for aviation. The Soviet Union began its own rocket aircraft programs, though these remained highly classified and wouldn't become publicly known until years after the war. Lieutenant General Mikhail Gromov, who had initially dismissed American rocket experiments, revised his assessment after personally examining captured German technology and reviewing American development programs. The rocket propulsion represents a fundamental advancement in aviation capability. The Americans understood this earlier than we did. Their hybrid approach, combining conventional engines with supplemental rocket power, is more practical than the German pure rocket fighters. This is a technology we must develop, or we will fall behind in air superiority capabilities. Soviet engineers faced the same fundamental challenges American engineers had confronted. Rocket propulsion offered extraordinary performance, but required solving numerous technical problems. Fuel systems had to be reliable and safe. Engine systems had to withstand extreme temperatures and pressures. Aircraft structures had to handle stresses far beyond conventional aircraft. And pilots had to be trained to operate aircraft with performance characteristics completely unlike anything they'd flown before. But was this technology actually effective in combat, or just impressive in testing? You're about to find out, and the combat results were more dramatic than anyone imagined. The combat effectiveness of rocket-assisted American fighters was demonstrated during the final months of the European War. Several P-47M squadrons, equipped with experimental rocket boost systems, engaged German jet and rocket fighters in combat, providing the first real-world validation of the technology. The tactical advantage was exactly as theorized. When radar detected high-altitude German fighters approaching bomber formations, rocket-assisted P-47s could climb from escort altitude to interception altitude in a fraction of the time required by conventional fighters. This dramatically reduced the window where German fighters could attack bombers without facing opposition. Captain William Hoved, who flew rocket-assisted P-47s in early 1945, described a typical interception. We received radar warning of German fighters at 35,000 feet approaching our bomber stream. In a conventional fighter, reaching that altitude from our escort position at 25,000 feet would require 5 to 7 minutes of climbing. By then, the Germans would have already attacked and disengaged. With rocket assist, we reached interception altitude in under 2 minutes. The Germans were shocked to find us waiting for them at altitude. Several turned away without attacking when they saw us climbing toward them at impossible rates. The psychological impact on German pilots was significant. They had become accustomed to American escorts being unable to reach high altitudes quickly enough to interfere with attacks. The sudden appearance of American fighters at altitudes that should have been safe created confusion and hesitation. This psychological factor was as valuable as the actual interceptions. The rocket-assisted fighters also proved effective against German jet aircraft. The Messerschmitt Me-262 jet fighter was faster than any American piston engine fighter in level flight, but its acceleration and climb rate were inferior to rocket-assisted American fighters. Several Me-262s were shot down by rocket-boosted P-47s that climbed to intercept positions impossible for conventional fighters. Lieutenant Robert Johnson recorded one of the first victories by a rocket-assisted fighter over a German jet. The Me-262 dove through our bomber formation and accelerated away. In a conventional fighter, pursuit would be futile. The jet was simply too fast. But I activated my rocket boosters and climbed at maximum power while turning to cut off his escape angle. My climb rate was so extreme that I actually gained altitude while turning, which shouldn't be possible. I intercepted him at 28,000 feet as he was pulling out of his dive. He never expected an American fighter at that position and altitude. I fired from 300 yards and saw strikes along his fuselage. He went down smoking. These combat successes validated the concept, but the technology remained experimental and problematic. Rocket systems were maintenance-intensive and unreliable. Several aircraft were lost to rocket malfunctions, the specialized fuels required complicated logistics, and pilot training was extensive because the handling characteristics during rocket-boosted flight were dangerously different from normal flight. So what happened after the war ended? Did this technology disappear, or did it evolve into something more? Hang in there. The post-war development might surprise you. The end of World War II didn't end rocket aircraft development. Instead, it accelerated dramatically as captured German technology and personnel were absorbed by both American and Soviet programs. The competition between these former allies would drive rocket and jet aircraft development for decades. The United States Army Air Force, which became the independent United States Air Force in 1947, continued aggressive development of rocket-powered experimental aircraft. The Bell X-1, powered by the same XLR-11 rocket engine that had been tested on wartime fighter aircraft, became the first aircraft to break the sound barrier in 1947. This achievement was only possible because of the rocket technology developed during the war. The X-1 program proved that rocket propulsion could push aircraft beyond the speed of sound, which was considered impossible by many aerodynamic experts. Captain Chuck Yeager's historic flight demonstrated that the wartime investment in rocket technology had opened entirely new realms of flight performance. Subsequent American rocket aircraft pushed progressively higher and faster. The X-2 achieved speeds exceeding Mach 3. The X-15, which flew in the 1960s, reached speeds exceeding Mach 6 and altitudes above 50 miles, technically reaching the edge of space. These research aircraft provided crucial data that informed the development of spacecraft and hypersonic weapons. Soviet rocket aircraft programs followed parallel paths, though information about them remained classified until the collapse of the Soviet Union. Soviet engineers had studied captured German technology extensively and recruited German rocket scientists just as the Americans had. Soviet experimental rocket aircraft achieved remarkable performance, though they remained highly classified. The MiG-105, a Soviet rocket-powered spaceplane developed in the 1960s, demonstrated that Soviet engineers had mastered the technology that had seemed impossible just 20 years earlier. Soviet test pilots flew rocket-powered aircraft to extreme altitudes and speeds, developing capabilities that would eventually enable Soviet space achievements. But the pure rocket-powered fighters, like the German Me-163 that had inspired so much development, proved to be technological dead ends. The operational limitations were simply too severe. Short flight duration, dangerous fuels, complex maintenance, and limited tactical flexibility made pure rocket fighters impractical despite their impressive performance. Instead, jet engines became the dominant propulsion for operational fighters. Jets provided good performance without the severe operational limitations of rockets. By the early 1950s, both American and Soviet air forces were transitioning entirely to jet fighters. The rocket-assisted hybrid fighters that had seemed revolutionary in 1944 became obsolete almost immediately after the war. Yet, rocket technology didn't disappear from aviation. It evolved into new applications. Rocket-assisted takeoff systems continued to be used for heavy aircraft operating from short runways. Strategic missiles used rocket propulsion. Spacecraft depended entirely on rockets. The technology developed to make fighters climb faster led directly to humanity leaving Earth entirely. Modern military aviation still uses concepts pioneered by those wartime rocket experiments. Thrust vectoring, where engine exhaust is directed to provide extreme maneuverability, is essentially a refined application of rocket control principles. Afterburners on jet fighters are conceptually similar to rocket boost, providing short-duration thrust augmentation when maximum performance is needed. Are you ready for the final revelation? Don't miss this. We're about to tie together what this technological race reveals about innovation under pressure. The broader lessons from the rocket-assisted fighter programs demonstrate fundamental principles about technological innovation during wartime and the nature of aviation development. First, the programs proved that desperate circumstances drive radical innovation. In peacetime, the idea of mounting volatile rocket engines on piloted aircraft would never have received funding or approval. Safety concerns and engineering conservatism would have prevented experimentation. But wartime necessity broke through these barriers. When conventional solutions proved inadequate and lives were at stake, engineers and pilots were willing to attempt approaches that seemed insane under normal circumstances. Second, the rocket fighter programs demonstrated that technological development isn't linear or predictable. The wartime rocket technology didn't evolve directly into operational fighters as initially intended. Instead, it branched into experimental research aircraft, strategic missiles, and eventually spacecraft. Technologies developed for one purpose often find their most important applications in completely different domains. The engineers trying to make fighters climb faster accidentally helped create the space age. Third, the American versus Soviet approaches revealed fundamental differences in design philosophy that would characterize Cold War technological competition. Americans favored complex systems with maximum performance. Soviets favored simpler systems that were practical and maintainable under field conditions. Neither approach was inherently superior. Each reflected different priorities and operational requirements. Major General Frederick Borum, who oversaw American rocket aircraft programs after the war, articulated the long-term significance. The rocket fighters we developed in 1944 and 1945 were operationally unsuccessful. They were too complex, too dangerous, too limited in tactical utility. But they taught us what was possible. They proved that aircraft could fly faster and higher than conventional aerodynamics allowed. They provided data and experience that informed every subsequent development in high-speed flight. The X-1 that broke the sound barrier was a direct descendant of those wartime rocket fighters. The spacecraft that put men on the moon used propulsion principles we first tested on P-47s in 1944. Failure in the immediate tactical sense led to success in the broader strategic and technological sense. Soviet assessments reached similar conclusions. Marshal of Aviation Pavel Zygarev wrote in classified post-war analysis, "We initially dismissed American rocket experiments as impractical and dangerous. We were correct about the immediate practicality, but we underestimated the long-term significance. The Americans understood that exploring extreme performance, even with impractical systems, generates knowledge valuable for future development. This is a lesson Soviet aviation must internalize." The transformation in Soviet thinking about radical aviation technology was profound. The same engineers who had dismissed rocket fighters as American excess in 1944 were developing sophisticated Soviet rocket aircraft by the 1950s. The skepticism had been replaced by understanding that pushing technological boundaries, even when immediate practical applications are limited, drives progress in unexpected ways. The young pilots who volunteered to test rocket-assisted fighters in 1944 were confronting mortality in completely new ways. They weren't just facing enemy fire, which all combat pilots accepted. They were testing fundamentally unproven technology where the aircraft itself might kill them regardless of enemy action. This required a different kind of courage than conventional combat flying. Captain Harold Fisher, who survived several rocket-assisted test flights and later became a test pilot on the X-1 program, reflected on the experience decades later. Flying rocket aircraft was accepting that you might die from engineering failure rather than enemy action. We were volunteers because we understood the importance. Someone had to determine what was possible, what worked, what failed, and how pilots could handle the extreme performance. The data we generated, often purchased with injuries or lives, advanced aviation in ways that weren't obvious at the time. The legacy of those wartime rocket experiments extends far beyond aviation. The engineering approaches, testing methodologies, pilot training techniques, and data analysis methods developed for rocket aircraft influenced every subsequent high-performance flight program. The cultural acceptance of extreme risk for technological advancement, controversial as it remains, characterized American aerospace development throughout the Cold War and beyond. The aircraft that Soviet observers initially dismissed as examples of dangerous American excess proved to be harbingers of technological revolution. Those temperamental, dangerous, operationally limited rocket fighters were clumsy first steps toward capabilities that would eventually put humans on the moon, create intercontinental ballistic missiles, and enable routine access to space. The story of rocket-assisted fighters demonstrates that innovation often looks absurd before it looks revolutionary. The Soviet engineers who laughed at American pilots strapping rockets to fighters in 1944 were designing their own rocket aircraft within a decade. The technology that seemed like desperate improvisation proved to be the foundation for capabilities that would define the rest of the 20th century. If this story of technological desperation, unexpected innovation, and the rocket-powered origins of the space age captivated you, hit that subscribe button now for more untold stories from history's greatest technological leaps. Don't miss out on the next revelation.